Thank you so much for your introduction. First of all, I would like to express my gratitude for all organizers to giving us a chance to share our research. So actually, Dr. Kato was supposed to be here, but he's not feeling well, so as his co-worker and his wife, so I will present instead. And actually, I hope I can doing well, but in case I don't, actually I would like to remind you that I am 8 months pregnancy, and I'm carrying the tiny future scientist, so there is excessive responsibility, right? So no pressure on me. Okay, so today's topic is triacylglycerol hydroperoxide analysis. So which is not the plant topic, but so as you know, the triacylglycerol is the main component of food lipid, and the prevention of its oxidation is very important to maintain the food quality and safety. So today's topic, I would like to introduce our analytical method for the triacylglycerol hydroperoxide (TGOH) analysis to determine the oxidation mechanism in the vegetable oil. And also, I would like to show the secondary oxidation product analysis to show how affect different oxidation mechanism to give the quality of the vegetable oil. So I think, as you know, the consumption of vegetable oil is globally increasing these days. And since triacylglycerol, TG, main component of the vegetable oil, usually possess the polyunsaturated fatty acids such as linoleic acid, LA, and alpha-linolenic acid, ALA. So that's why it's vulnerable to the oxidation, which causes the oil deterioration. And once TG is oxidized, TG hydroperoxide, TGOH, is generated as a primary oxidation product. And then the TGOH is easily decomposed to the various carbonyl compounds such as aldehydes, and which cause oil browning and bad smell. So as you can see, so because the TGOH is very active, so that's why the prevention of the first step, I mean the TGOH generation, is a key to maintain the oil quality. So I'd like to talk more about the TGOH generation as a first step. So regarding the oxidation mechanism, there is two types. One is a radical oxidation, and the second one is the singlet oxidation. We call also the photo-oxidation. The radical oxidation is caused by the heating or just exposure to oxygen. I think while you are cooking, the radical oxidation is occurring in your oil. And another one in the singlet oxidation, the ones photosynthesizers, such as the chlorophyll, are excited by the photoirradiation. So it transfers excited energy to oxygen and generates singlet oxygen, which is very active oxygen. So because those oxidation mechanism is totally different, that each oxidation generates specific TGOH isomers. By the radical oxidation, those 4 TGOH isomer is generated. Actually, I'm showing the linoleic acid TGOH isomers. So the oxygen is inserted to the 9 or 13 carbon of the linoleic acid. And the cis-trans and trans-trans, the isomer is also existed. So that's why those 4 isomers. As for the singlet oxidation, addition to the 9 and 13 position, 10 and 12 hydroperoxide are also generated as shown here. So importantly, the antioxidative measure is totally depending on the oxidation mechanisms. So for example, vitamin E or polyphenol is quite effective to the radical oxidation, but not so effective for the singlet oxidation. So carotenoid or just shading is just more effective to prevent the singlet oxidation. So therefore, to choose the suitable antioxidative measure and keep the vegetable quality, the determination of the oxidation mechanism is very, very important. So that's why we thought that by analyzing those TGOH isomers specifically, we can determine what oxidation was occur in the vegetable oil. So, but of course, those TGOH isomer is exactly same molecular weight with similar structures, so that those analysis was very, very challenging. Here is the MS spectra of the different hydroperoxide positional isomers in the general method. The proton adduct parent iron gives the exactly same product iron, even though parent iron is different isomers. So which means this MS method did not allow to analyze the hydroperoxide positional isomer specifically. But fortunately, so Dr. Kato found that in the presence of alkali metals such as sodium ion, the hydroperoxide positional isomer give unique product iron. This is the 13 and this is 9 hydroperoxide. And as you can see, there is totally different product iron pattern, right? So which give us information that what positional isomer in it. So this principle, so we propose that this sodium ion would react with the hydroperoxide as a Lewis acid. As a result, the coordinated bond of the sodium ion with the oxygen and double bond here. Lipid hydroperoxide generates the hydroperoxide group position-specific product iron, as shown here. So which means we can determine the lipid oxidation mechanism by the analysis of this product iron. Actually, by using this principle, this method allows us to analyze the hydroperoxide positional isomer of the various fatty acid with the many ester form. Like this is a EPA and arachidonic acid 1 and DHA and denonic acid 1 in the phospholipid and the cholesterol ester. And then actually we apply this method for the various sample. So today I would like to introduce the method application for the TGOH analysis in the canola oil. In this study, we focus on this TG molecule, which has the 2 oleic acid and 1 linoleic acid, LA. So because this TG molecule is the main TG molecule species of the canola oil. And then we analyze those isomeric structure of the LA hydroperoxide for the determination of the oil oxidation mechanisms. So first, sorry, this is busy slide, but we synthesize the TGOH isomer as shown here. The LA linoleic acid was oxidized, and then we got the 6 kinds of the isomers. And because hydroperoxide is very active, so we protected by using the methoxypropane. And then those isomers were esterified to the triacylglycerol. And then we got 12 isomers. Those numbers shows each positional hydroperoxide isomers, and prime means the alpha position isomers because TG has the SN isomers, so that's why we have 12 isomers. And then we purified and got the pure TGOH standards. And by using these standards and also the specific product irons, as I introduced before, so we optimized the LC-MS method, and this is the chromatogram of the prepared TGOH standards. In the presence of the sodium ion, TGOH positional isomer are clearly distinguished as shown here. So moreover, in this condition, TGOH number 1 to 6 and those alpha and beta position were clearly analyzed. So even those as exactly same molecular weight with unique, quite similar structures. So then we applied this method to analyze the marketed canola oil. So in the fresh canola oil, which was before the shipping, so the TGOH, there's two types of the TGOH, which is number 2 and 5. So which means that the fresh canola oil has slightly oxidized by the radical oxidation at low temperature. And then we bought the same canola oil in the grocery store in the center city, and right after open them, we analyzed the TGOH isomers. Here's the result. So interestingly, TGOH isomers in marketed oil was number 2, 3, 5, and 6. So it is suggested that marketed canola oil is oxidized, mainly singlet oxygen, which means photoirradiation during the shipping or just selling leads those oxidation. So please image your canola oil in your shell. So actually, I believe it's packaged in a clear bottle. And usually canola oil contains a trace amount of the photosynthesizer, such as chlorophyll. So it is really vulnerable to photoirradiation. If the photoirradiated oxidation than we expected. So now then I would like to move on to the next topic. So as I described above, so we successfully developed the analytical method for TGOH isomers, which can determine the oxidation mechanism in the edible oils. The elucidation, at the same time, the elucidation of oxidation mechanism provides another really important information. That is the kind of the secondary oxidation products. Because the secondary oxidation product structure are depending on the TGOH positional isomers. Because since the dose bond is pretty weak, so it's decomposed from near the hydroperoxide position. So that's why those carbonyl compounds those carbonyl compounds are more volatile and affect the flavor. Actually, when we oxidize the canola oil by heating or singlet oxygen, the photoirradiation, actually the flavor is totally different. Actually, I hope you can try. And for the radical oxidation one, the smell is like food, like tempura. And by the way, please try the tempura while you're here. And if you don't know the good place, I know the many places, so please let us know. And so as for the singlet oxidation, oxidized canola oil is like I don't know how I can explain, but I know that my brain says just don't eat it. It's like a chemical smell. Anyway, you can try. And so that's why we analyze those secondary oxidation products. And actually, but there's so many compounds. So today, I will just focus on the secondary oxidation product of the acrolein. Actually, I think, as you know, the acrolein is one of the highly reactive aldehyde, which highly reacts with the protein and DNA. So many studies suggested that its involvement with various pathogenesis. And so far, the radical oxidation of alpha-linolenic acid, ALA, are thought to be a main source of the acrolein. So this is a reported pathway. So the main source is alpha-linolenic acid, ALA, of the radical oxidation. And generally, it has been said that linoleic acid, LA, is not a source of the acrolein. Recently, we expected the decomposition pathway of each lipid hydroperoxide, and this is the expected decomposition pathway of the La12 hydroperoxide, which is a singlet oxygen-specific specific hydroperoxide. So this is pretty busy thread. But surprisingly, we found that this singlet oxygen-specific La hydroperoxide generate acrolein here. So nevertheless, it is said that acrolein source is mainly radical oxidation of ALA. So actually, so far the photo-oxidation was not taking account for the chlorine generation. So that's why we did hypothesize that photo-oxidation LA hydroperoxide can be a source of the chlorine. And similarly, we also expected that the photo-oxidation of ALA also increased chlorine generation compared with the radical oxidation. So to prove the hypothesis, that each LA and ALA hydroperoxide isomer was thermally decomposed. In the agreement with the previous study, radical oxidized LA did not produce the chlorine, but as we expected, singlet oxygen-specific LA hydroperoxide indicated by in the red definitely generated chlorine, and the amount of the chlorine was comparable with that of ALA. So more about chlorine generation from the singlet oxygen-specific ALA hydroperoxide shown here as in red. So about 2 times higher than that of the radical oxidation ALA. So this data demonstrated that singlet oxygen oxidation promote more the oxidation generation. And this phenomenon was also observed in the edible oil. We used the canola oil, rice bran oil, soybean oil with a different amount of the fatty acid composition. So those sample was irradiated at the 500 Rex for the 7 days, and control was placed at the dark place. So after that, the oil was heated at 180 degrees for 90 seconds, and the chlorine is analyzed by the GCMS. And surprisingly, chlorine was increased from the photo-irradiated edible oil in time-dependent manner. Even the rice bran oil, which contained a low amount of ALA, generate the chlorine comparable with the soybean oil, which contains a high amount of the LA and ALA. So this means that LA can be also a source of the chlorine. So because photo-oxidation is directly affected by the presence of the photosynthesizer, such as chlorophyll, so the amount of the chlorine should be considered with not only the photo intensity, but also the presence of the photosynthesizers. So here is a summary of my presentation. So our analytical method allows us to analyze the TGOH isomers, which give the oxidation mechanism. And more we expected, edible oil are affected by the photo-oxidation despite of its unopened. Moreover, we demonstrated that photo-oxidation of LA and ALA can be also a source of dark chlorine. So here is my take-home message. Please store your edible oil at the dark place for sure. Okay, that's all for my presentation. Thank you so much for your attention.